e to the x squared, exactly. Now here's the thing. There is nothing algebraically you can really do to that easily. E to the x squared, does that equal e to the x squared? No, it does not. When you have powers of powers, what do you do with them? Multiply them. This equals e to the 2x. Is e to the 2x the same thing as e to the x squared? No, there really isn't anything you can do other than to make an observation. You have the same bases here. You have this base right here and you have this base right here. You understand that? So one way to think about this is, as x gets big, how big does x squared get? Much bigger, right? So the whole top here is going to get big, but the denominator is going to get much, much bigger. So this thing is getting something smallish over something huge is going to what? It's going to 0. Another way to think about it is like this. This right here is equal to the limit as x, it's equal to, this is a limit law, but it's okay if you don't write it. This is equal to e to the limit as x goes to infinity of x minus x squared. And the reason this is helpful is because of this. X minus x squared, what is that going to as x gets really, really big?
0.
No. Negative infinity. It's going to negative infinity, right? So this is going to e to the negative, you can't really write that, I'm cheating here, right? But what does that mean? What is e over that? What is that going to? 0. Exactly. That's another way to think about it. The point is, there isn't really a concrete way of doing this. We can try doing something different, though. Let me show you. You want to do something like this. You don't know what this equals, right? X equals limit is x infinity of x minus x squared. That equals, we don't know what it equals, so we'll say it's equal to question mark. Okay? You could take the natural log of both sides. So we could do that. You'd have ln, and keep in mind there's a natural log of the limit as x goes to infinity of e to the x minus x squared. What is that going to equal? Ln of question mark. We're going to solve for question mark eventually. And the reason we do this is, what's the cool thing you can do with exponents inside logarithms? You can bring them to the front, exactly. And you can massage this a little bit. This is not a trivial thing, but you are allowed to do this. You could take this limit and switch the order here. So you can rewrite this as the limit as x goes to infinity of what? The natural log of e to the x minus x squared is equal to ln of question mark. Now what can you bring to the front? X minus x squared. So you can have the limit as x goes to infinity of x minus x squared, right? Of the natural log of e equals the natural log of question mark. Are we okay with that? What is the natural log of e?
1.
It's 1, exactly. That's 1. So you have the limit as x goes to infinity equals the natural log of question mark. Oh, sorry, I forgot the middle part there. Of x minus x squared equals natural log of question mark, right? Well, what is this limit equal to? What? Negative infinity, right? What is ln? Ln is log base e. This is log form. You have to go to exponent form. I realize many of you might not remember that, but this means that e to the negative infinity equals question mark, which is equal to 0. That's one. This is a hand waving, not 100% correct, but you can use this. This is way more work than you need to do. What I would expect on a test is you literally could write out the sentence like the denominator is getting much larger than the numerator. So this is going to 0. You literally could write that at this point. I would not expect you to use this. This method is sometimes very, very useful when you can't logic it out. There are certain times when you must get that. You have to deal with the exponent and you have no way of doing it. And taking the natural log of both sides will help. This is not one of those times where it's too beneficial. We got the same answer, but it was a little bit more work. And it is much easier to see a common denominator in this one when you factor it. This turns into the limit as x goes to 1 of 1 over x minus 1 plus 1 over x minus 1 times minus 2. What do we now multiply this first fraction by? We have to multiply by a form of 1, right? So we end up with the limit as x goes to 1 of x minus 2 plus 1 all over x minus 1 times x minus 2. What does the numerator simplify to? x minus 1 over x minus 1 times x minus 2. Now, what's that magical thing that happens right now? Leaving you with just 1, so you end up with the limit as x goes to 1 of 1 over x minus 2, which is equal to negative 1, which equals negative 1. This one is entirely, can you add fractions? The limit as x goes to infinity, what do you end up with? You get x squared plus 4x plus 1, right? Correct? And then you get plus x and then minus x, so minus what? Minus x squared all over this thing, which you can't do anything with. Correct? What happens to the numerator? What cancels?
Wait, is that supposed to be squared?
Nope, because square root times square root it goes away. What cancels? So you're left with the limit as x goes to infinity, of x goes to infinity, 4x plus 1, right? All over this thing. Now, what do you have to do to attack this one? It was someone said it as the first thing they thought you should do. What are you going to multiply by? What are we going to multiply by? 1 over the square root of x squared. 1 over the square root of x squared. Why do we do that? Because the top turns into 4x plus 1 over this. And what's the bottom turn into? Well, it turns into x squared plus 4x plus 1 plus x all over square root of x. Can we simplify that a little bit? Sure. The limit as x goes to infinity of 4x over x plus 1 over x. Because what's the square root of x squared? This one turns into the square root of x squared plus 4x plus 1 over plus x over x. Can we simplify these a little bit? So the last thing we end up with before we actually finish this is 4 plus all over the square root of 1 plus 4 over x plus 1 over x squared plus 1. Why did we do that? X is going to infinity. We just broke it down into its simplest limits we possibly can. What happens to this one? What does that go to? 0. What does this go to? What does this go to? You're left with 4 over the square root of 1 plus 1 is equal to 2. Done. This one's challenging because you take a flat limit. I call it flat. There's no fraction here. That doesn't seem like there's anything you should be able to do. Well, you unflatten it. You break it down to its individual pieces, and the limit is definitely 2. You could get an idea of this if you did what? Let's say you had no idea what to do on this. Let's say you saw this thing. What's one thing you can always do? You could graph it and take a look, and it would go really, really close to 2. When you make an estimate and the estimate is really clean, when you make an estimate and the estimate really looks like it's 2, what does that say about the scope of the algebra? What does it usually mean is true? There's a way to do it. There's a way to do it by hand. Whenever you get a clean answer like 2, there's probably a way to do it by hand. Probably a way to do it by hand. Estimating this right here. We've been trying to find the slope of tangent lines, right? Yes. What's one way we have been calculating the slopes of tangent lines? What's one way? What have we been doing? Give me a complete sentence. Anybody that just gives me a noun gets to leave right now, okay? I want a complete sentence. How have we been calculating slopes of tangent lines? That's a noun. Give me a complete sentence. Yes. Close to it, exactly. We've been taking a single point like this, called maybe x, f of x, and what have we been doing with f of x and this point right here? We measure the slope of the secant line. And then what do we do after we do the slope there? Choose another point closer. Which point stays the same? A, f of a stays the same. So this is anchored, and we take this point and we move it, and we keep on repeatedly doing what? Measuring secant line, secant slope, secant slope, secant slope. So we have a path. We've used our calculator to create tables. So if we have those 2 points right there, can you tell me what's the slope between those 2 points? F of a over a minus x. Another way to write that, what's another way to write that same exact thing? F of x minus over, it's the same exact thing, right? So that's the slope of the secant line. which ones have been fixed, meaning we're not moving them. We aren't moving this value, right? Yeah. Which values are moving, or which one value is moving? The x value is moving, right? And what is x doing if we're estimating this limit? X is going to, it's increasing, getting closer and closer to a. So what have we done repeatedly? We've done the limit as x goes to a of f of x minus f of a all over x minus a. Okay, so this original graph right here, this green line represents position. What does the slope at this point represent? What does the m value, what does the slope at that point represent if the original graph is position? What does the m represent? It represents what? Instantaneous what? Instantaneous what? If you can't use the word velocity, what would you say? Instantaneous? Nope. Instantaneous of instantaneous rate of change of position. Instantaneous rate of change of position. You know that as what? V of t. So this represent, if I got m there, that specific m would represent the velocity at the point a f of a, or at the time, what's the time value in this case? A. We haven't specified one, it's general. Velocity is speed plus direction. Velocity is speed with a direction. Is this ringing any bells? How many people have taken physics at some point in their life?
I forgot everything.
Yeah,
Nice!
suppressed memory.
Nice. Okay. So, what kinds of questions can I now ask you? I can ask you this question. What is a nice graph to work with? Let's work with, let's say, y equals x squared. Is that okay? Give me 1 point on y equals x squared. That isn't boring. That's boring.
1/2, 2/3.
That's not quite right. 8 and 64. Let's go 3/9. How about that? Yes, that was arbitrary. Okay. I could ask you, for example, we could now estimate what is the slope here. I could also ask you, let's say you had the slope and the point. What could you find? If you have a point and a slope, what can you write? An equation for that line, right? So one thing I could ask you is, what is the equation of that line I just drew in there? You have the point. What do you need? Slope. That's it. If you got another point, that would be great. But do you have another point? No, you don't. You have a point. You need a slope. How are we going to find that? Well, we're going to use the limit method we just used. M is equal to the limit as x goes to a of f of x minus f of a all over x minus a. In this case, what is the a value? A equals 3. What is f of x? No, x squared. What is f of a? 9. 3 squared is? So now we fill in the blanks. M is going to be the limit as x goes to 3 of x squared minus all over x minus 3. This is a limit which we can solve. You know how to do this. What would be your method of attack? What should you do? Factor. So m is going to equal the limit as x goes to 3 of x plus 3 times... I mean, the first thing you do is you try to plug in 3. Can you plug in 3 right there? No. So this cancels. Oh, now you're left with the limit as x goes to 3 of x plus 3, which is what? 6. So if that's the slope and our original point was 3,9, can someone just tell me what is the equation of the line? Raise your hand and just tell me what the equation of the line is. The point is 3,9 and the slope is 6. What is the equation of the line? Someone raise their hand and tell me off the top of their head. Just tell me, what is it? Overthinking it. Make it easier. Make it easier. Make it easier. Y minus equals
6.
Done. Stop there. You do not have to put things into slope-intercept form if it's not asked for slope-intercept. Why do you feel the need to write things in slope-intercept form?
Because we've always learned that.
You've always learned that. That's how you first conceptualize lines. Ready? You don't need to go any further anymore. Stop here. What is this form called? Point slope. Stop here. You're all done. That is point slope form. That's totally valid. Stop it. Stop it. Now, how could we visually check this? Well, we could type into our calculator x squared.
That's so fancy.
Oh, look at it. We could type in our calculator x squared, right? Can you plug in point slope form into your calculator? No. Your calculator needs what? Slope intercept. So what did I do over here? If we go back here, y equals 6x minus 18 plus 9. Y equal, don't move because it means nothing, right? Same thing, right? Take a look at what this is. Does it look like it's the tangent line? It really looks like it. Now, here's the thing. Is your calculator super good at making judgments like that? Not really, because your calculator has really, really poor what? Resolution, right? That being said, that's pretty good because here's a warning sign. Let's say you came up with the equation for a line and it did this. Is that a tangent line? No. Does this look like it could be a tangent line? Yes, absolutely. So what's the first part of your homework for tonight?